Vector addition problems. We're going to look at a couple of problems which involve the addition of vectors. Firstly, an aircraft needs to fly east and can fly at a speed of 250 meters per second in still air. If there is a 100 meter per second wind blowing in a northerly direction, in what direction must the aircraft fly to reach its destination, and what would be the velocity of the aircraft relative to the ground? Well, for a problem like this, it's essential to do some sort of diagram. I've started here with a baseline running east-west. This is the direction the plane actually wants to go in. Onto this we can add the 100 meter per second wind in a northerly direction. The aircraft wants to go east, but will also have to go against the wind, and so will go in this direction at a speed of 250 meters per second. If this is a scale drawing, you'd simply draw these two lines to the same scale, and you could then measure the angle and the length of this line, the velocity relative to the ground, which I'll label v. If you're doing a calculation rather than scale drawing, it's still worthwhile taking a little bit of time to make your diagram fairly accurate. It makes the problem easier to visualize and also gives you a quick check to avoid any silly mistakes in the calculations. Firstly, the question asks us to find what direction the aircraft must fly in. So I'm going to find this angle theta. I could equally find this angle. Cos theta is adjacent over hypotenuse, which in this case gives an angle theta of 66.4 degrees, which looks roughly right on my diagram. Just a quick check there. Meaning that the aircraft will set a course of 66.4 degrees east of south. Now to find the velocity of the aircraft relative to the ground. Well, you'll see in the diagram the resultant velocity, the one we want to find now, is going from the first tail to the last tip. We have the velocity of the air plus the velocity of the aircraft, giving our resultant velocity here. We can find this by Pythagoras. V squared is equal to 250 squared minus 100 squared, giving a velocity relative to the ground of 229 meters per second due east. Okay, on to the second problem. Two opposing rugby players are 25 meters from the touchline and 15 meters apart. If the player aiming to score can run at 5 meters per second straight towards the touchline, with what velocity must the defending player run to intercept him at the touchline? Well, again, a diagram is essential, and even if you're doing the problem by calculation, try to keep your diagram accurate. Here we've got the touchline and the first player 25 meters from the touchline. The second player equally 25 meters from the touchline and 15 meters from the first player. So the second player needs to go in this direction. That is distance d that we need to find. By Pythagoras, the distance covered by player 2 is equal to the square root of 25 squared plus 15 squared, a distance of 29.2 meters. Quick check, that seems about right, a little bit more than 25 meters. Now, the time he has to do that, well, player 1 is going to cover 25 meters at a speed of 5 meters per second. So player 1 will take 5 seconds to get to the touchline. Player 2 therefore also needs to take 5 seconds, so their speed will equal their distance covered, the 29.2 meters, over the time available of 5 seconds. So player 2 must run that bit faster at 5.8 meters per second. Don't forget we've been asked to find the velocity of player 2, not just their speed, and so we must also find a direction. I'm going to find this angle theta. tan theta is equal to opposite over adjacent, or 15 over 25, which gives theta 31 degrees. A quick look at the diagram confirms that that is roughly correct. So we can say that the defending player must run at a velocity of 5.8 meters per second at an angle of 31 degrees to the perpendicular to the touchline.